fundamental theorem of calculus say when you take the integral, a definite integral, right, what you do is you take the antiderivative of that function. See what I'm saying? No? Right. And then substituting the lower, I mean the upper value minus the lower value, substituting in all of that. But now the primary thing is that you got to understand that the relationship between capital F and F is that capital F prime, right, equals F. See what I'm saying? No? Or in other words, F here is the prime of capital F. So another way of seeing is right from the beginning, you can just state this theorem as capital F prime of X. But take the definite integral in abbreviation just simply Fe minus Fa. That's a different version of that. Slightly different way of how you're writing that. Okay? The point now is that taking the definite integral on any derivative, right? Taking the definite integral on a derivative function, it will come out being just the function value at the ending point and subtract the function value at the beginning point. Okay? And so from that realization, we come up with this what's so-called an F-change theorem here. Okay. Now, the integral, right? An integral here, I mean the definite integral of the rate of change. Integral rate of change is the net change. That is saying that when you take the definite integral on any derivative of a function, because derivative, right, is the rate of change. We've learned that from Calc 1, right? And so according to the fundamental theorem of calculus, this now makes sense to come out with, and as put it on the board earlier, the antiderivative of the rate of change is simply just the function itself, right? So now it's the function at b minus the function at a right here. And so this is rate of change, but the answer comes out right here. We call this it's the net change. Right? See, so make a note right here: FB minus FA. Right? It's just referred to as the net change. It has quite a few applications, actually. I mean, maybe for us, we only narrow down to one among the many applications. But think about the business people. Okay, for the application in business, right? There's a concept of a function that they call the cost. So cost being a function, right? And cost a lot of times depends on the number of units. X here is the number of units. Just think about that. When you're leading a factory right there, then you got to spend out money to produce X units, right? Say you're the iPhone company, for example. You got to spend money to produce those parts, right? So that's why its cost is a function depending on the number of iPhones that you're planning to produce. Okay, to manufacture. And when you after you factoring that, after the aftermath is that you're gonna go sell them away, you make revenue and all that, right? And then turn that into your profits. But at the deepest level, the cost here is a function depending on the number of units that you're manufacturing. See what I'm saying? No? But then a lot of times, cost as a function doesn't come out so easily. So people usually come up with people can easily measure the change of cost again, right? The rate of change again. And so this is the derivative of cost function. Okay. And then that can be easily obtained. It's just the way how it works out there. A lot of times we can observe the change And then we can observe that over time, so that's why we can quickly estimate and come up with the rate of change that we can easily observe, right? And that's why, so now think about, the reason I mentioned this is that think about if you already knew the derivative, right? If you already knew the derivative, and then you are asked to find, hey, find, right, the net cost, okay? The net cost between 1,000 units, right, to 1,005 units. Okay. A lot of time we change the number of we change our production level from 1,000 units to 1,500 units. Your company has a changing in plan like that. Hey, instead of manufacturing 1,000 units, okay, let's change to 1,500 iPhones, right? And so we can immediately observe the rate of change. But then, how much is the total change in cost? So change in cost is going to be the cost at 1,500 minus the cost at and then 1,000. See what I'm saying? But doing this work right here is essentially just the same as doing the antiderivative. I mean, doing the indefinite integral from 1,000 to 1,500 on the derivative function. Yeah. That's what it says. Okay. So that's just one application among the many applications out there. This one here belongs to the people, the world of the business experts. Okay, that's just one application. And for us right here, the closest example is about displacement. Okay. So displacement is when you're moving an object, right? You're moving from here to here. That's a displacement. Because you may go in a path like that, or you may go in a straight path, or you may go in a path like this. But in the end, moving a point from one place to another place, it's called a total displacement. See what I'm saying now? And it's got direction there. See, the path where you're changing it got direction and all that. And so, if displacement is being regarded as a function, what's the standard name for it? S of t. Okay? A lot of times people use S of t, the function of time, indicating your position. So, actually, I'm lying a little bit. Displacement is not quite that. Displacement is a change in position. Sorry, I'm taking it back. The change in position. So think about when you see you have some starting position right here. You have some starting position, and you're ending at some final position, right? Then yes, you may have some displacement by going in that path, or you may have some change of position by going a straight path or going some other crazy path, whatever, right? But then so the change in position, so rate of change, right? Rate of change in position over time, like that, right? It's exactly what we call the velocity. You change in position over time. We call it as a rate of change in position. Or another way of saying that, the displacement, we put that over time, we call it as a velocity. So velocity here a lot of times is indicated as a function d of t. And so in that way, and I talked earlier about position being a function s of t, then velocity will be the derivative of the position function. Okay. Because again, it's displacement, how much change in position, right, over time. Okay. And then instantaneously it becomes the derivative. Change of position or displacement, right, over time. That becomes velocity. Right? The instantaneous velocity. And so a lot of times out there, we got devices and we got machines that we can monitor the velocity. We can monitor the changes, okay, over a certain amount of time, and then we can approximate, and we can come up with velocity function easily. But then from velocity function going back to find a position, that's where we need this net change theorem here. right? So that we can take take the integral, the definite integral between a certain number of time like that, right? And that gives us the net change in the positions, and the net change in position, we call that as the total displacement. Okay, and so let's apply that into a problem here. So let's look at the problem. I'm still leaving it here on the screen. But what you have here is a velocity function. Right? What we have here is velocity function. It's the rate of change, the instantaneous rate of change of position function. Right? It's not the beginning position function. And so v of t equals t cubed minus 36t. How did it come like that? We think about we got some machine device that measure the change in position of a device and come up with that function right there for us. And then the time interval is anywhere from between 5 seconds to 9 seconds, right? And so now, question A, we want to find the displacement. Okay? So displacement, in my explanation earlier, displacement here is the change in position. Right? It's the change in position of the particle. So we want to find the change in position over on that time interval from 5 up to 9. See what I'm saying? No? And so that means in the way how we're understanding the problem, then the displacement that we're looking at right here, the displacement that we're calculating, truly is that s of f of 9 minus s of 5, and we know this result by the net change theorem. And actually, it's not yet the net change theorem. It's just the way it is over the interval. Then because s of t is the position function. So by the way how we understand about displacement, the displacement on that interval is simply the position at 9 seconds minus the position at 5 seconds. Okay? But then keep in mind right now we don't know the position function. This position function we have right here is unknown. So that's why to get this precise answer right here, because if we know the function, the position function, doing this subtraction is easy, right? And there's no trouble at all. But the problem is we don't have the position function. We only have the velocity function. And so to find this, right? S9 minus S5 right here. Okay. The way to do that, according to that change theorem, all you do is just take the definite integral from 5 to 9. See what I'm saying? Huh? Right, of your velocity function in respect to t. Right? And then your velocity function here simply comes out here. Okay, so from 5 to 9, and it was t cubed minus 36t. Okay, that's how we do that. So this starting point right here is guaranteed by the net change. We know we can find that value, right, by doing this integral here. Are we good with that? And of course, the displacement here, we realize the displacement here is a net change, right? Net change in position. That's what it is. So now that we're just simply going to take the antiderivative work and all that, right? Because the antiderivative is not necessarily it's not exactly the position function, because antiderivative is just a family of the whole of so many different functions having this velocity function being the derivative, right? So there's a constant difference. That's why when you take the antiderivative and then evaluate it, it will get you this displacement, but in the end we still didn't have to find out exactly the position function, what that is. Right? Because it's still different by a constant c. Okay. So now that goes t to the fourth times 1/4 minus, and then that's a 18 t squared, right? And we're evaluating from 5 to 9 then. Right? Like I said, see, right now we got the antiderivative, but somebody may have questioned me, so how come you don't find the position function by setting that equal to this, but not necessarily, it's not really equal to the 1/4 t to the 4th minus 18t squared, because the antiderivative could be, I mean, the actual one here could be some of that plus with some constant. See what I'm saying? No, it could be different. So it's not necessary to find the actual position function. The point is just to get the antiderivative right out of your velocity function, which is right now being understood as a rate of change function. Okay. And so now go ahead and do the calculation. Okay. Yep. You're gonna get you're gonna have a 1/4 times 9 to the 4th minus an 18 times a 9 squared, right? And after that, we're gonna do next one here is going to be a 1/4 times 5 to the 4th, right? Minus an 18 times a 5 squared. Okay. Go ahead and help me out with that final calculation. Okay. And so now let's look over to part B of that example. So, this is the question for part B. And so now the idea here is that so I've made it as an explanation yesterday that displacement is the net change in position, right? So, got a quote position here. Got a position there, different position. Right? Any of these 2 points, you can call them an initial position or a final position. So going from here to there, that's one path. So the total change right here is displacement. We've seen that yesterday. Displacement, and then we put that over time, right? We come up with what's so-called velocity. So if position is a function, we're looking at position being a function of time, S of t here, then velocity is a lot of times instantaneously, velocity is a derivative of our position function. But then this question here now talks about speed, right? It's the concept that a lot of times we mix up the two right there, but they're not really the same. So then a lot of time, so before we get to speed right here, I have to point out for you, displacement itself here, a lot of times is being mixed up with the distance traveled. Okay? So displacement is similar, but it's still quite different with the distance that you have traveled. So think about a situation like this. I mean, I pointed out 2 points in a plane position like this, but even in a simpler situation, you got a point on a line right here, right? And you move into another place right here. So just simply from the initial point ending at the ending point, you got a displacement. But here's the thing: as far as the path that you have gone, sometimes here's the thing: you may have gone all the way past that point and come back. See what I'm saying? Huh? So really, the total distance you have gone is not exactly the same as the displacement. Right? The total distance that you travel, even on a straight line like that, right? There's a point here, and there's the end of the seat, like that, right? The end of that table, I may walk way past, right? And then I come back, so really my total distance that I walk is a lot more than just the displacement. See what I'm saying? Okay. And then sometimes I even do this. I'm starting out at a point on the same line path here. I walk all the way there and then turn all the way back here. Okay? You pass that initial point and come back to that initial point. So total displacement is still that net amount right there. But as far as distance, really, we've gone that far distance. That much up, that much way back, and then another distance back here. See what I'm saying? That's why a lot of times distance is being misunderstood to be the same with displacement, but now in real physics understanding, right, it's different. Okay. But then, so the distance that you have traveled is also some kind of changing position, but it's not the same as displacement. I have pointed it out. It's all positive amount. That's one thing. Distance have to always be positive quantity. And then, so, now, when we go distance, how far we have traveled, we put that over time, okay? We put distance over time, and this is the little kiddos have learned in a very early age that the distance over time, we call that the speed. You want to say, no, right, about third grade or fourth grade, they start teaching you, how fast you walk, right? How fast the car runs right there. See what I'm saying? But that early concept being taught there is really indeed just the speed concept right there, because we play with the simplest the side of that. We put the distance, right? The actual distance over time. So it's speed right here. But then, so at that point, you can see speed is quite different with velocity here, because velocity has, velocity, first of all, it's displacement over time, so it got directions evolved again. Okay, whereas speed here, we just count the absolute positive distance that we travel over time again, how much distance we've made over time. And so in that way right here, you guys will have to wait until calculus 3 to have really all clear of that. Because right now you don't have much, I cannot assume you have any kind of background with vectors. And even if you know something about vectors, it's not the formal learning at this point yet. And so you're going to wait until the calculus 3 to see this information I'm about to tell you. But at the most basic right here, speed and velocity in the end is still related, okay? With your known velocity function being the v of t, the instantaneous rate of change of displacement. We're talking about speed will be the absolute value, okay? Velocity can be negative, because in the same thing about on the same line, on the same linear path right here, it matters between how fast you go, but forward, or how fast you go backwards. See what I'm saying there? Okay? And so that's velocity, it has direction involved. But now speed, no matter which way you go, we just want to find out physically how fast, how much distance you're making over time. And so at the most basic round right here, speed is related with velocity, but in a sense that speed is the absolute value, right, of your velocity function. See what I'm saying there? Right? So take that. But then if you're really asking me, questioning me like at the very deep level, like why does it have to be so, and proving it out to every little detail of that, you're going to need to wait until you learn some more about vectors, okay, to get that clear understanding. You know what I'm saying? Yeah? And so now, and by the way, back to these kind of problems, we don't deal with the kind of going crazy path on a plane or anything like that. Yes, we just stay on the simpler side of that, moving on a straight line path again. Okay, but then there are already so much directions involved, and so in that way. And I'm going to put it in its separate column for you. So speed is velocity, right? In absolute value. And we already knew that velocity is the derivative, right, of our position function right here. So in other words, speed can also be thought of as the s prime of t, but in absolute value, right, the derivative of your position function. So it's all starting out with position. Changing positions, changing between positions, we call that the most raw form is the displacement, right? And then distance travel is the positive version of that. Think of it that way. And then so speed is the absolute value of velocity. And so now we take that understanding and we bring that in here. So for part B of this problem, right? See, we want to find the distance. The distance. Right? So, very analogous to the displacement. We've learned that displacement, right? Displacement we've learned from part A right here is simply just it's because it's the net change, right? The displacement is the net change in the position. And we found that by doing this definite integral for part A, velocity function. That's the general idea we did in part A. So now we're taking that analogous idea in here. Speed, distance, can be found by taking the definite integral of your from the inside over your interval, but on your speed function, which is the absolute value of your velocity function again. Okay. So that's the major difference between the two formulas. To get displacement, we just simply find a definite interval right now from your given velocity function. But now for distance, you have to take the definite interval out of your absolute value of your the absolute value of your the velocity function. Okay, and so that means now you utilizing that formula into our problem. We're going to do the work as follows. Distance, right? Just from A to B, but then maybe there's going to be some big amount of distance traveled. So we'll go the interval from 5 to 9. Your interval here is from 5 to 9, right? According to the problem. Right? So that with that interval, I'm going to produce my speed function as t cubed minus 36t. Right? In absolute value, that's the truest sense you get. Okay. But now that's the idea about absolute value function. You guys have to understand one thing. When we're learning, since our beginning day and then up until this point, we've gone quite some distance in terms of the taking definite integral, but we will never have a direct method to find definite integral on a function that involves absolute value. See what I'm saying? Up to the newest point that we have learned, and yes, fundamental theorem of calculus say anytime you find the definite integral of a function, right? The first thing you do is get the antiderivative. You guys follow it? Okay, and then do the substituting in. But how do we get antiderivative out of an absolute value function? We haven't done so. We haven't learned how to do so. And as a matter of fact, we will never know how to handle absolute value function. Okay, and finding antiderivative of absolute value function. So we put up that. And that's the reason why we've got to play some trick. So the main idea now is that we've got to find a way to get this expression outside of the absolute value. Or in another way of saying, we've got to find a way to get rid of absolute values, but still maintain the positiveness of our velocity function. You got the idea? Right? Absolute value is in that purpose to force everything to become positive. But is there any way that we can deal with the function without absolute value but still maintain the positiveness of that? Am I making sense with that so far? Right, and that's the idea. And so now algebraically, I want to bring up something for everyone. It's another algebra property that it's okay that it's faded away. It's easy to understand, but then at point to point, I have to keep reminding you. Anytime you have an absolute value expression, right? And you want to get rid of the absolute value, then you got to follow the rule over here. If the expression x inside of your absolute value, the expression, that's what I meant. Okay. X could be t cubed minus 36t, or x could be e to the x, whatever crazy expression. The point is, if the expression inside of the absolute value by itself is a positive or at least zero value expression, then you can just simply get rid of absolute value, and the two expressions will equal. Okay? But on the other hand, if for any reason you know that your expression inside of the absolute value will be a negative quantity, that's why here to be specific, if the expression is negative expression, known to be negative, I should have put the if there as well. Okay? Then to get rid of absolute value but still maintain the positiveness of your final expression with you have to put minus sign there. Okay? See what I'm saying there? Think about it in the simplest case. Absolute value of a negative 5 here. In the end, it comes out 5, right? But how do I see that to be consistent with this? That is simply because now, basically at the end, purpose right here, at the end, I removed the absolute value. But then the way of doing that simply because my expression inside here is negative, less than 0. You guys see what I'm doing there? So to come up with a final expression without absolute value, what I did there was a negative 5, and I put a negative sign in front of that. And that cancels things out right there, right? And making it positive. That's another way of seeing that as a general expression without absolute value. So you guys should have learned this back in algebra, but very understandable that faded away quickly. Trust me, I've taught algebra all over as well. Students hate that property. Okay, they just don't want to use it. But at some point when you guys have managed this far, we have to keep getting back and use it again. See what I'm saying? No? Right? And so, and that causes some impact for the problem that we're about to do here. Because at this point right now, we see in this expression, it's all over. We don't know where this expression is negative and where this expression is positive. That's what the problem is. So, let me bring that in on the screen right here. Now have a look at just the function itself right here. X cubed minus 36x. 36x. Okay. Hide away all the bricks right here. The bricks. The arrows on. So putting that in a very far zoom with them. You can see that the function is doing pretty crazy, swinging up and down, right? Swinging up and down like crazy right here. Do we need the entire picture of the graph here, by the way, for the problem? What the graph you have here is the graph for the t cubed. Well, decimal is not graphing it with t, so I have to call the variable x again, right? But it's x cubed minus 36x. Do we need to use the whole graph for that function?
No.
Just for this problem? No, right?
Just go from 5 to 9.
Yeah, just go from 5 to 9. See what I'm saying? Just go from 5 to 9. And even if that interval from 5 to 9, 2 to 9 is not indicated for a function where we're talking about time, and the practical domain is only from 0 to wherever higher, right? Because our problem here has an intention. The variable here is intended to be time. So there's no such concept in our living life here as being the negative time. You see what I mean? Okay? And so in that way, but then Boz was right. Did I say your name right?
Yes.
Okay.
Yes, I think so.
Okay. But anyway, so that's why now I have a reason to only focus to that zone anywhere from 5 to 9. Okay? But now what's happening there? You see in between 5 is about there and 9 is maybe about there here, right? You see that that's where the problem is. There's some breaking point. And then in that interval from 5 to the breaking point that the function sinks below the x-axis, right? That means that the function does becomes negative in some interval between 5 and 9. There's some interval that the function stays negative. You guys follow it? And then there's some other interval from whatever that breaking point is, right, to 9. The function stays positive above the x-axis, above the t-axis. And that's where we're going to have to start being aware about that algebraic property. So, now with decimals here, I'm going to zoom it in a little more, right, for you guys to have a clear look. You see where that breaking point is? Right there in the picture? Okay, let me step out a little bit. That breaking point, right, 5 is here, the function is there. That breaking point is right at 6, right? So the graph is telling you that. See what I mean? Right. And so from 5 to 6, the function stays below the x-axis. Or in other words, that expression t minus 36t, t cubed minus 36t is a negative expression like that. That in that interval, right? Your expression is negative. But then in that interval from 6 to 9, right? It's positive. See what I'm saying now? So now here's the problem. In that way, consequently, bringing that into our function, we have to do some breaking up, right? Some breaking apart of our integral here. We've got to consider two separate functions. Like the area problem we've done before this example yesterday. We're going to have to produce one separate integral accumulating from 5 to 6 right here. Right? But we know that the function in this interval is going to be a negative. So to get it out of absolute value, this is what I'm doing. T cubed minus 36t, I'll put negative sign in front of that. Okay? See that there? Because that's the way how we're handling absolute value when, see, that's how we're handling absolute value. We're going to put negative signs, right? If the expression itself is known to be negative. See what I mean? And just now I have proven graphically, right? I have pointed out graphically that the function, this function right here, this absolute value function, right? The expression itself inside of this interval is negative. That's why to maintain the positiveness, I have to put the extra negative sign there. Does that now connect with that area problem with the orbital part of this problem? See, so at that point I jump straight into, hey, here you go. Anytime you graph things, you go the x-axis, right? We put a negative sign in that. That was because the main idea is we were dealing with absolute values of function. See what I'm saying? Okay. And so since you guys asked about that, and so it's worth to mention it anyway. So now in the next interval, from 6 to 9 over here, right? Then we know that the function, see, it was on that graph, it stayed above the x-axis, right? And that means that now we can just simply remove the absolute value sign right here without changing the sign. So TQ plus 36T, whoops, not plus, minus. But I mean, no extra negative introduced here. Okay. See? Now that will definitely give us two positive areas, and we're going to add them up together. And that will get us the total distance. Am I being clear with my explanation so far? And so in that way, now, why don't we divide responsibilities in? I need somebody to do this separate calculation, the accumulation from 5 to 6 here. But be aware that, after we account that negative sign here, your function turns into a minus TQ plus a 36T. Okay? Sign change again. So I need someone to volunteer on this particular one over here. And you guys have done fundamental theorem of calculus long enough, so I can leave that completely for you. Who would like to take this one? Thank you over here. And the next feature here has an area, but accumulated from 6 to 9, right? TQ minus 36T. Okay. Who can help me with this one? Who can volunteer with this one? And then the rest of you guys, you can go ahead and float them, right? Meaning you can double check on any of these results. All right. Calculation experts, what have you got?
For the negative, the negative one, I got 30.25.
30.5. Right. Anyone would like to double confirm that?
Yeah, I got 30.
Thank you. All right.
I got 506.25.
506.25. Okay. Anyone would like to confirm that? Seems to win it. You got that too? Okay. All right. And these are all meant to be positive areas, right? Because of that triplet that now the total of the two total areas. That will give us the final speed, the total distance that you travel. So that means at the end of your distance, come out being 536, right? 0.5. And the units here say in meters, right? That's quite some distance. See what I'm saying there? And so, but for you guys right here, being a calculus class right here, I will have to point out for you a couple things as well. Think about when you're working with a problem like this, right? When you're working with a problem like this on a test, and unfortunately, graphing technology is not immediately available. Put yourself in that scenario right there. Is there a way we can detect where the interval? Because mainly, what I brought up here is that mainly for one problem, right? When you're dealing with that absolute value thing, even that you need to detect which interval your graph falls below the x-axis, meaning negative, right? And in which interval your graph falls above the x-axis, meaning positive. I'm talking about in case you don't have access to a graphing device, right? To pull out the graph, how can we detect?
Do the number line thing.
The what thing?
What do you call it? The goofy number line. You do like 0, 1. You do like all your x-intercepts on one line, and you do the positive negative.
Yeah.
What?
Yep.
I don't think that's what it's called.
It's related to that, but
Yeah,
he's right. Yep. Well, it's not that goofy. Okay, here's the idea. So I'm talking about, let's forget about the graph, okay? It's some fun stuff. The first thing is to detect where it intersects with the line. Because, right, once you intersect, once you have recognized where it intersects with the line right there, then it's going to switch into, positive, negative around it, right? And so, right there, the interval is 5 to 9. Okay? But at least you have seen through the graph some explanation the function goes up and down, right? But those points right there, we call them the x-intercept. See what I'm saying? No? So how do we find the x-intercept? We set the function t cubed minus 36t equals 0. That's the pre-calculus stuff, right? Which is set because the function itself comes out, the function outputs come out meaning being the vertical value. So we want the vertical value equals 0. That's why we set the function, right? Equals 0. And we want to find out, hey, which t variables, right? Which value or which values of the t variables, right? Giving us 0 outputs, 0 y value. Sounds good to them? Okay. And so in that way right here now, you also need to have produced for yourself an equation to solve. And of course, trust me, at the level that you guys are learning right now, it's more about understanding the meaning of these problems. So no professor is giving you like terribly hard problems so that it takes you hours and days to solve just an equation like that. So usually something will come very clear. Like say, for example, with this equation, you can just simply factor it out, right? You do the factoring. There's a t and then a t squared minus 36. Okay. And then I keep sharing with everyone here that I have a favorite identity that I use is, see the difference of 2 squares? So you go, so the t factor is there, of course, but the t squared minus 36, I see that as a t squared minus 6 squared, so difference of 2 squared here. So I have t minus 6, and in parentheses, a t plus 6, equals 0. And now I have completely factor my left-hand side expression, right, of the equation there. And then solving that right here, it gives me for this function, it has 3 x-intercepts. T equals 0, even though I call it t, but I call it x-intercept. T equals 6 and t equals negative 6. See what I'm saying now? But then the interval that we're working with is from 5 to 9, so do we need to take that guy? No, so we have outright to rule it out, right? Do we need this guy? No, we have outright to rule it out because the interval we're working with is only from 5 to 9. So now we only take t equals 6. Sounds good? And so clearly 6 here is that I call it, it's a breaking line, right? It's a breaking point where it switches between positive and negative. I mean, it could also, somebody in my other classes also ring a bell. What if it's like this? That's why it's best that we do the testing, the sign chart, that goofy thing that was saying like that. Okay, so let me tell you, it's not that goofy. Okay. Yes, the idea is the sign chart. So you're substituting a test point, like 5.5, right? You put that test point into your t cubed minus 36t. Do a quick calculation and identify what's the sign of your final output value again, right? In that interval. See what I mean? So go ahead and do a quick check right here. So 5.5, right? 5.5 cubed minus 36 times 5.5. What kind of value do we have here? Is that positive or negative? Negative, okay. There you go. So I'm not too worried about the actual value, but I'm more concerned about the sign again. So I know that my function in that interval, according to this test result, right, got to sink down negative. Sounds good? Okay. And then you guys can do the other one. Go ahead and do the other one. Now I'm talking about we're detecting the positive and the negative intervals completely without looking at the graph. Right? You guys see the process now? Positive, right? That's why it's once again it comes back and be consistent with our results we've had over here. Okay. Now knowing that this quantity has to be negative inside of that interval, right? We do that treatment. Okay. And then knowing that the interval inside of the absolute value will be positive in that interval from 6 to 9. That's why we can just simply drop the absolute value sign, right? Without imposing a negative sign in front. You got the idea? Okay. So you guys are being ready for any situation. If the instructor allows the calculator, I mean, if I'm allowing the calculator, then you use your graphic calculator, quickly put it out, right? So that you can know where it's negative, where it's positive. But who knows, maybe calculator you're going to meet a different instructor and he's expecting, that you guys know how to detect these, so you put out a graph. And that's the way it goes. Good? And you just got to be ready for anything. All right.